Uh, for coming, for what is of us that have crossed in on the hour of the morning. But I have good news. You're at no risk of falling asleep. Okay, because I have a very exciting talk prepared for you. In fact, I think danger of actually overstimulating you, such that you're compelled to run in the room with the canal with your mind flame with new ideas. So I'll do my best to avoid that, but no promises. Okay, EGRAPHS and automated reading. Look back, look forward. This is what we're going to talk about today. Different approaches to equational reasoning, simplification. In particular, I want to talk about completion. Now, equation. And I'm going to describe how the mind, a different perspective on the EGRAPH that's really changed how I look at the and the union mind is ground atomic completion. And then the next step, how an EGRAPH is ground completion. And how perspective leads to solutions to problems that people that the EGRAPH has difficulty. And great that. And in general, think about take on the ground in automated reasoning. While the traditional has mostly been applied to theory proving, I think sort of the EGRAPH community has shown that these techniques are all helpful in compilers and simplifiers. And so generally speaking, just like keep digging through the literature and you'll find all sorts of systems that are applicable just in the context that the original authors didn't. Okay, so equational reasoning was there. The simple idea there. It's where you have some sort of tree, or crazy data structure, and you keep doing that. Is 0, you find that syntax, play with A, bother adding 0 at point. And really, it's not it's kind of like the 80% solution. It's like what makes the world run in terms of simplifications. It's fast, as fast as it can possibly be, right? Just like finding a taking it, boom, that's like really fast. It's also simple, which is, really good. People come up with this, go study with monks on a mountain in order to understand, simplification. This is like, this. So it's been around. I mean, you can't really like find like it doesn't even make sense. There are some bad aspects to it, and there's the rule interaction / conflict, maybe is what you might also describe this as, and that's where you can have different rules can apply in 2 different ways. Matters, and that's because the top, the probably everybody here and probably you want to do a shift by that. But if you have a multiplication and then a division, you the tab A. But you accidentally apply a shift now the second apply and you get the version of the program. So the order you use these rules matters. Non-termination is another issue. Maybe a little more theoretical. In practice, what you can do is just put it in a limit and it won't terminate. It is sort of of waste. If you're just going, you're not really and yet you don't want to remove these non-rules because they have a lot of interesting things. So you're sort of in a tough situation. And then sort of related to the first 2 is incompleteness in the theorem to or suboptimality in the simplification, where the speed is removed. I'm talking about sometimes you have to come up a valley, up a mountain, way up a mountain, to find a deeper valley on the other side. And greedy simplification is never going to do you. Okay, so what else is out there? EGRAPHS. Good. Also, I think, and part of the graphical picture I'm going to show on the slide, everyone probably on their talk, everybody's seen. And so they're simple enough that you don't need to, again, study the fundamental or to understand EGRAPHS. I can show people that picture and explain sort of happening there. It's declarative-ish. It's a little bit declarative than greedy, but not completely declarative. Sort of, you know, the operational character. Right? How about that? And that's both good and bad. You can sort of tune. It's still operational, and you can interpret kind of what's happening and sort of think about where sort of graph, but it's sort of character. It's more greedy simplification, but more declarative simplification and a little less operational greedy simplification. And it's fast. There's a very fast simplification available, egg, and you can make these things really hum. They are not as fast as greedy simplification. And a plethora of applications, which we're going to hear about today, but doing it for compilers, optimizing algebra expressions, optimizing linear algebra expressions, different theorem proving applications, application website list of them. Two main modes, and use here those two main usage modes, reasoning even in particular. Another term, and I want to know that's equal. So it's take two terms, now it's a other mode, optimization is a simplification mode, where you put a term and run for a while, and then you get a term as good or better as the thing you put in, with guarantee that it's equivalent. And sort of traditional automated reason, I think, focuses on the first mode and emphasizes that mode. That's almost the only difference between what we're doing and what the automated reasoning community is doing, is that they focus on the first mode and don't focus on the second mode as one. So here's the diagram. You know, I'm not going to belabor this. We've seen this, but if you assert all these equations, you can assert them into the EGRAPH. You can start with this graph at the term on the left side, and as you assert this, you move to the right, and then once you end up finally with the equation, you end up at that final EGRAPH. So it has this, it corrects the order in respect. Arguments that are equation reasoning. Sort of three areas you can talk about. The first is paramodulation, which came and I think the basic idea is that, okay, instead of going greedy simplification, just like mutating a thing, what if it search instead? So if you have some term, you can apply some equation, you can copy that term, and then you can get a copy of that term when you find the equation. And this big set of terms equivalent to the original one, just expand that. You'll find everything. In addition to that, paramodulation comes up with resolution theorem proving, which from the get-go is about clauses. It's about a clause of positive and negative literal. And so from the get-go, paramodulation condition, breadth first character, also has a conditional or contextual character, where you can be under the assumption of particular qualities inside the clause. So then next thing that happens is completion, which is about 70s. And the idea there is you have a pile of good pile of equations. That's what I'm trying to do. So if you can get a terminating complex system out of a pile of equations, you've just destroy it, and you do it kind of. In addition to that, completion of the is the ability to sort of like equations that implied by particulars, you can reduce and simplify your equational arrangement for reasons we'll see. More thing combination of these superposition is causal. It's a thing that's something about causes the way the relation was, but it's a strong notion of assuming useless equations, so limiting sort of spraying of this first search, and really cuts down on the search space. Okay, so completion, which I'm going to focus on today. It's equation rule, which means terminating and confluent. And when I heard of completion, I was like, I don't know about this. Like term confluent, I don't really know what that means. I'm busy, but I've come to understand that it's a very interesting algorithm, and they're terminating the most pragmatic way of describing what's going on. For me, an early stop, okay, confluent in a given fashion, particular equation to prove, and confluence that particular goal equation is simplifying, and it becomes trivial if it's like, and that actually did all the way to the if I improve the goal before that, I'm good. That's all I cared about. And sort of in a similar fashion, you can use in a simplification-driven manner, where some term I'm trying to say, choose, and I'm turning my equation into a forward not entirely right system, which is going to do a better job simplifying than the original random pile of rewrite rules I derived from the or just find equations. So you can use it in both these ways. Not guaranteed actually for every possible case, but you always be sort of making some kind and completion is and it's kind of equation to orient a equation, you orient it using term order. Basically, an idea of what it means for one term to be simpler than another. It actually comes up in the context of termination, which is a more theoretical thing to consider. The sort of can't anymore. But a little more these real variables. Okay, so that are complicated, but you can tell that when we shift by one, we kind of want left shifting. Yeah, left shifting. So this equation to convert those. And then the second step is you find failures of confluence. These are their possible phase ordering problems. And let's see where the left-hand side of the rules overlap. I go this way, or I go this way. And equational this way and this way. And you can just add your equation set. And the third step is you reduce the equations with respect to your current rewriting rule set, which is filling up with real rules like completion. And I can this way. Trivial, throw them away. But if they think trivial, back and over again, sort of force phase order. Make describe this as moving equation between the occasional set and the rules. And rules basically simplify the rule. If I keep a rule that is implied under one tracer, I can remove that jump using simplify and R simplify rules. It's really great for compaction, sort of a canonical rewrite system thing. This is an example using G, a theory for regional logic. You can download it. I didn't write it. It's round completion, Haskell. It's like naive implementation, like tune. It does pretty good in the cask unit inequality region. Here's an example. I have these two rules, x by 2, and I can do that. I can throw this in the tree, and this there's a bit of what I did is I put a tree and tree dump holding rewrite stuff, which is useful. And this is the it's not true. And if you look at these rules, the phase sorting problem is fixed here. Have to apply the rule first. This gives you two rewrites that does things. Work, but in this case it did. Okay, so the second is time completion. So you can find hash cons roughly, and so we can talk about union finds as a stepping stone to the EGRAPH. With pointing up to the parents, which to the top up that is, and that is a common at class. All the inverted system where the rows are a and a circle. Another inverted is a common terminating strategy. This binary to basic properties of those binary functions. So, this operation is the thing. Find and so this chart the system system equation incrementally to our confluent terminating then completion is the same thing as calling union, okay? And the simplify rules that let you get rid of sort of junk is the thing that can dignify path compression in a union find. You can directly talk about those rules that can dignify path compression. And this is the point where maybe a different point that term ordering is sort of related to time breaking that you do in union find. When you call union, you change pointers up to the parents, and then you make of those two canonical lists. That's how you call union. And then structure versions you supposed to all the parent relationships the trees flat. But you might want to do as a break maybe in some way makes it more deterministic or invariant the order that you applied union, or an EGRAPHS just like the oldest or the latest one, they have reasons to think maybe that less updates happen or some performance reason they might prefer that. And so that sort of deterministic tie breaking is more like what's happening in the writing version, where you pick a priority and ordering by atoms, and so I tie break using that. I throw this into tree, A equals B, C equals D, that's what it's like, you know, objects can't destroy the inner parts. Make this unit equational problem, this atomic equation problem, and is this system here. And if I chart that, if I have a little diagram of that, where the rewrite arrow I'm representing as red arrows. You can see the forest, and the root of that left equivalence class is A, and it's fully compressed. That's the thing because it's the fully chewed on rewrite system. And A, D, and E are in the same E class. A and D are in the same E class as F. And also note, so you also have proof reduced. If you look at here, it actually how A is in the same E class as E, step by step referring to Chewy is kind of the best proof automated in terms of readability, kind of like greatness. Just a side note, I love Chewy. So EGRAPHS completion. Let's step up a notch, right? Now we don't want to comic, we want to talk about terms. An EGRAPH is a completely reduced ground rewrite system. Type checks, sense checks, maybe let's not bring type. Because ground completion solves the pile of ground qualities. Just that ground completion works, and that sort of demonstrates once you know that, it is a corollary that it is decidable that equations is a decidable problem. You can sort of add anything you want to that. Likewise, EGRAPHs solve the pile of ground inequalities. Okay, so they're solving the same problem. They kind of seem like the same thing. And here's the chart corresponds to this. The canonical term that the term writing system rewrites to is the same thing roughly as E class. You can sort of associate them with each other. R simplify can dignify canonization of the EGRAPH. Run it. Now this is a little interesting, a little twist. If you like the correspondence that the term orders correspond to the abstraction objectives, so basically you want to rewrite the simpler things, and running the rules is the same thing as calling extract. And make the correspondence just a ticket. If you like the multiplication of 3, the shift of it away to 1, that exactly corresponds to the notion of weights in sort of the mainstream extraction algorithm. So these two really do correspond to each other. Okay, so we can take that pile of equations that defined the canonical egg EGRAPH example, you know, multiplying A shift to 1, you discover the pile of equations, you assert it, and I've also put a start artificial large, just a bit like on the hand side of my favorite rules, just so I can track that. And then I throw it into Tree, and Tree gives me this, and this is the resulting right system. And it shows the starting term, the best term you got is actually A. So if you called extract starting thing, you're supposed to get A as the best thing. And then here we go. Okay, so wake up. If you've been sleeping, I don't think you've been sleeping because loud. This is inside the talk, okay? This is the money. So that is exactly the equational system I got out of Tree, copied verbatim, just so you can look at it. And then I wrote a program that converted, I got as a bunch of tuples in a Python program to that diagram on the left, okay? So that is, you know, mechanically produced from this. And again, just like the union line, the red arrows are the rewriting arrow. And now let's talk about some distinctions, somewhat crucial, between the egg diagram and this diagram. Okay? We have to see where the E classes are, because anything connected by arrows are the things that are in the same E classes. This A corresponds to this node A in some sense. This division node corresponds to this division. This multiplication corresponds to this multiplication. We can see they're connected by red arrows. They're all in the same E class. Okay? But terms, these are nodes. The children of these the class, the E class interaction. The children of these point to other terms. Okay. In addition, these arrows are directed. These red arrows directed, and that's something that's not here. The EGRAPH is a lossy version of the diagram that loses that directionality. Maybe for good reason, but maybe not. And keeping that directionality sort of, I think, enables you to do more subtle things. So take a beat, soak it in. That's the diagram later. All right, where are the E class E nodes? You actually keep the correspondence closer and the basic flatten. So you can introduce a fresh constant for every term and then make those less in the term ordering. And so the way that works, if I had foo is baz bar equals bar, I invent new atomic constants called E1, E2, E3, E4, such that this thing's in flat form. And then when you orient the things are less, okay? So now it looks kind of like this. And I'll note that there are two kinds of rules that go there. Rules of the application to a bunch of E and rewrite to some other E-class like thing. And that directly corresponds to the E-node table. And the other type of rule is rewriting E-classes to other E-classes, and that directly corresponds to in the way I talked about earlier. Now, some more observations. This flattening transformation is not obviously possible for notions of scope or context. If you have some variable in scope or something, and now you try and break this thing apart and flatten it, you can't sort of communicate that in scope to like the sub-pieces. Maybe a solution to that is something like slots, which is going to be talked about later today, where you add arguments to your E-classes. Does that have well-behaved properties? I don't know. Also note that, as I said, eGraph is sort of a sub-based. You can also think of completion an eGraph with fancy capabilities. So the eGraph features of having universal/unification variables / all variables, or a notion of first-class rule that's like right into the eGraph. Completion is an answer to that. Maybe it's not the perfect answer, maybe you want something a little more, but it is an answer to that question. And also I've brought it quite close to a thing talked about in the past, tree automata. A way of formalizing what tree automata are is it's a finite state fold over a tree. And so you can describe that by the pile of term rating equations where you say, like, if state Q1 and Q2 come into a cons node, switch over to state Q2 here. And if I rewrite Q as E, then you can see that's the same thing as I was talking about with the flat form before. So there's a strong relationship there. E-matching can be done directly in the rewriting form. Really, I think the intuition is that an E-class in a traditional eGraph represents, in some sense, possibly an infinite set of the nodes of the terms that would like collapse into that E-class. And you can generate that by sort of like seeking down through the children of the E-nodes in there. And that's sort of what top-down E-matching is doing. And you can do the same sort of thing. What's the funnel of terms that goes into a canonical element? Well, you just run the rules backwards. That's the thing that'll just generate all the terms that end up at this canonical element. So that's how you can do that. I don't know if there's top-down and bottom-up versions, and I wish I had a whole talk that I could give on bottom-up E-matching because I think it's great. It's the simplest form of E-matching. It's simpler than top-down. You completely guess each pattern variable, and then what you can do is you only need to build upwards. And because you only need to build upwards now instead of expanding downwards like you do in top-down E-matching, it plays nicer with theories because, for example, if you have a set that's like permutation invariant, if you're going downwards, you need to guess which permutation you need. But if you're going up, you can just sort the thing because you have everything grounded. So that's sort of why it plays better. And perhaps it's related to the AE graph. So there's a notion in automated reasoning of strategies. And there's like incomplete but pragmatic limitations you can have on resolution or superposition. And in particular, the set of support is one to point out, strategy, where you separate your axioms into a pile over here and a pile over here. And you only allow inferences that have at least one member from this pile, okay? And so that's similar to separating out rules versus the eGraph, where you want to sort of bring together a fact from the eGraph and something in your rules together, and you're allowed to do that. But you're not allowed to just churn on the rules in and on themselves. So that's a way of thinking about how you can map equality saturation back into completion using the set of support strategy. Generally speaking, also prolog and datalog can be thought of as strategies, incomplete strategies on resolution. So there's a chart of propositional versus equational automated reasoning you can make. Prolog is like functional logic programming, datalog is like egglog, ground ordered resolution is like an eGraph / ground completion / ground superposition. And then there's a bunch of question marks there. Food for thought. Making a big chart and seeing some question marks, empty boxes, is a good stratagem for like coming up with things to do. So, all right, what does this have to do with the mysteries and promises of context and lambdas and destructive rewriting? Chui already has a notion of context. Oh, 5 minutes. Oh, okay. Well, I can slow down. All right. Chui already has a notion. There's a paper here, Efficient Encodings of First-Order Horn Formulas and Equational Logic. That's the Chui authors. And it's similar to assume nodes, where they sort of encode a notion of conditionality using if-then-else expressions into standard completion. It's in Chui today. Chui today has a contextual union find if you just write down those axioms, and you get the result. It is a thing that's like a thing that did rewriting under context. And but with sort of an interesting distinction that actually it does a way better job of cleaning up the junky assume nodes because they're not needed anymore. And it actually does it by asserting into the eGraph a good or not the eGraph, sorry, the completion rewriting rule set, an ability to like clean up those unneeded pieces. Also note that ground superposition is also a notion of a contextual eGraph. So you can think of, so ground superposition is clauses. You're talking about clauses. And so this is a clause here of not u is equal to v or r, which is maybe another equation, for example. And you can rewrite in there, and that's sort of what superposition inference rules look like. And using the classical correspondence that not A or B is the same thing as A implies B, I can write that equally in this form. So now it really looks like there's something contextual happening there, that you're under the assumption u equals v, and I know r, then I can sort of apply another equation I have over to the side, s equals t, and sort of chew in there. And there's more rules in superposition. And ground superposition is going to be terminating, but it's closely related to SAT. So it might be quite brutal depending on what you're doing. But again, maybe horn clauses are kind of the thing we're the most interested in, and maybe there's a better story if you specialize to that. Chui has a story about horn clauses. In terms of lambda, there is recent work for lambda superposition and supporting higher order logic in automated reasoning systems. These are complicated papers. I don't entirely understand them. I've been trying. I'll continue to try. This whole project sort of started with me trying to take the stuff that's in zipper position off the shelf and just use it without understanding it, and I just sort of burnt out. But they have a solution. There's reason to believe that things aren't going to be as clean as they are in the first order ground case. But in some sense, these systems, if you could get at the right pieces today, have something akin to a lambda eGraph in them. They have some sort of solution to this. Maybe it's not perfect in every possible way, but zipper position and E and vampire have systems in them like what you'd want for a lambda eGraph. And I'll probably continue working on trying to tease that out and figure out where I can get the interfaces like for Chui. I haven't figured out the equivalent interface that I have for Chui for these systems. And finally, destructive rewriting. This sort of correspondence between completion and eGraphs gives us a line of attack of how you can talk about destructive rewriting in a principled way. And I think basically it's combination problems is what you want to talk about, which are horrible things, and basically they never do it that you want them to do, I think. But the question is, under what conditions does completion of ground rules, which is basically ground equations, which is what the eGraph is, combined with actual rules, and presumably a good pile of actual rules, rules that on their own would be confluent and terminating, under what conditions does the combination of those and the completion of that combination stay well behaved? I've tried talking to my local term rewriting expert, and he doesn't really know. But maybe it's out there in the literature, and if you know, please tell me. But I think that's a way of formulating how you can talk about destructive rewriting in a principled manner. And so I've sort of covered the main points of the talk. Union finds and eGraphs can be directly related to completion. It's a slight, subtle, but very important shift of like what that diagram means. And I think the diagram is crucially important for understanding. Clues to lambda context and destructive rewriting. This stuff is great, but there's specialized problems here that the general automated reasoning systems don't need to, they try and be as general as possible typically and complete as possible. And we're interested in less complete things and very special ground horn versions of these things. So I think there's a lot of opportunity for fast implementations and things that people can pull off the shelf and just like use. And that's something I'd like to seek out in the future. And again, simplifier-oriented automated reasoning is kind of a bullet point here. Well, it's a bullet point on the slide, it's a bullet point in the talk. Thank you. The abstract's available. a lot of what I've said here is in these 3 blog posts. These are great references on this material. And these slides are on the PLDI EGRAPHS website, and also the abstract is linked to, which has, it goes into a little more depth. Thank you.
Okay, thanks, Phil, for the very enlightening talk. We have time for 1 or 2 questions from the audience.
I don't know how big this is as a question, but one of the things that stuck out on the most important slide was you mentioned how the red edges are directed. And that feels like a notion of refinement rather than equivalence. This also comes up with tree automata. I was wondering if you've thought about that, right? Like I might, like contextually maybe x over x is equal to 1, but 1 is always, out of any context, a refinement of x over x, for example. So yeah, I don't know if you've thought about refinement. I mean, it's tricky because it's not symmetric, so.
Yeah, that makes a lot of sense. I've been trying to think about this in particular because I've been trying to figure out encodings to just like not have to look at the deep innards of these or weird interfaces of these tools. I've been trying to figure out encodings that I can directly get simplification out of stock vampire or stock E. And I think that relates to refinement in the sense that I need to sort of talk about the cost of the terms internally. And the cost, it's kind of equational, but kind of not. This is also shown up in egglog, where really you want it to be a lattice of costs when you're actually trying to talk about cost inside the system. That was a pile of whatever. But yes, I am aware that refinement is a very interesting issue and is kind of crucially important for compilers and things because they're not really equational. They're actually refinement relations as you're going from a less defined program to a more defined program. I don't have a good answer, basically, is long short, but I agree that it's a good question.
Okay, I think we should move on to the next talk, but as Phil said, a lot of this content is on his blog, and if you haven't seen it, there's a lot of great food for thought there, so make sure to check that out. All right, let's thank Phil one more time.